Hello, everyone. Welcome to my talk on incorporating external knowledge through pre-training for natural language to code generation. We always have the dream that one day we can tell our computers to write programs for us. So today we are tackling the task of natural language to code generation, which given a natural language intent, we want to output a code snippet which can achieve this intent. In our case, we use Python, for example. With tree-based decoders, the output code are usually syntactically correct, as the example here shows. With a copy mechanism, we can see that the variable names, such as the text here, are correctly generated. However, many API calls, functions, and classes are not seen in the limited amount of human annotated training example. For example, the re.sub are incorrectly generated to decode.translate. To solve this, we come from the intuition that human annotations are limited and costly. For example, the English to Python dataset Konala has about only 2,700 pairs. We want to incorporate external resources automatically in the model. Naturally, we come upon two sources. The first is Stackoverflow website, and the second is the Python API documentation. Our strategy is to first pre-train on automatically processed external resources and then fine-tune on human annotated data. The first resource we use is the mined data from Stack Overflow. Take a look at this screenshot from Stack Overflow. We can treat the question as a natural language intent and the answers snippet as the target code. For the second resource, we use the official Python API documentation, which contains class methods and other top-level functions. We can treat the natural language documentation as the intent. However, the methods here shown are usually function signatures, which are not real usages. So we need to pre-process them to emulate the real usages by filling the arguments and variable names. The problem with API documentation is that the data distribution mismatch problem. The pairs from the API documentations cover each API function only once. In real programs, however, some APIs are used more than others. For example, the curses library has much more APIs than the JSON library. However, the JSON library is used much more frequently. This would cause the model to bias towards the modules with more API functions, which is not realistic and will probably hurt the performance. Our proposed solution is that we first estimate the real distribution based on the real usage statistics estimated from annotated pairs as well as the mined pairs from Stack Overflow. And then we use that to resample the API functions to generate the data for pre-training. In our experimental setting, we base our model on a state-of-the-art natural language code generation model called Tranks. And we use a human annotated dataset called Konala, which contains 2.3K training pairs and 500 test pairs. For the Stack Overflow pairs, we use top 100K pairs ranked by the mining score, so they are of relatively high quality. And for the API pairs, we obtain about 12K pairs parsed and preprocessed from the Python API documentation. Let's take a look at the results. If we only use the Konana manually labeled data to train the model, we achieve about 27.2 boost score. If we add manually, we, we add mined data, about 15K and 100K mined data, you can see that the more mined data, the better. However, if we add in the API documentation as is, it will cause a performance drop, which is partially caused by the distribution mismatch. After applying our resampling technique, we can see the increase in the performance. We also find that resample by code retrieval is better than resampling by intent retrieval, which actually kind of makes sense because the code is the target of the generation in our case. We further apply hypothesis re-ranking, and we find that the improvement is orthogonal to our proposed strategy. Let's take a look at several generated examples here. For example, open a file f.txt in write mode. We can see that our proposed model can correctly use the W argument. In other more complex cases, we can see that the existing model struggles to get the correct API generated. In our case, we can use the re.sub and random.choice, which might be learned from the API documentation as well as the mined data. You can see that in general, we have better argument placement for APIs and a better selection of which API call should be used for a certain intent. To conclude, we have several major takeaways. First, adding external resources, which is basic data augmentation, helps even though the data are noisy. Second, be careful about the data distribution mismatch, and sometimes retrieval and resampling could really help. Our code and data are publicly available, and we also have a web demo for you to try out. Feel free to reach out to me if you have any questions. Thank you.